All right, let's go ahead and get started here. All right, we've got a solid number of attendees here. Thank you very much for joining. This is webinar number 2 in the series of 10. This is our 2021 Apex webinar series. Today we'll be talking about mid-surfacing and shell meshing of complex geometries. But before we get into that topic, I just wanted to give everybody a reminder of what this webinar series is actually about. You can see here that we are on number 2. We are in March, we're talking about best practices, mid-surfacing, and shell meshing, but this is really the best practices series. So what we did is we contacted a number of our strategic customers and partners around the world, and we said, what do you guys want to know about when it comes to Apex? And these 3 best practices webinars came up: geometry cleanup, mid-surfacing, and shell meshing, as well as dynamics, frequency response dynamics analysis. So those are the 3 that we'll be talking about. The next series of webinars that you guys asked for was an interoperability series. As you know, Apex is more than just a preprocessor for MSC Nastran. It is a platform for a number of different tools, and 3 tools specifically that you, our customers, asked for and continue to ask for is: how do you use Apex with Patran? How do you use Apex with Atoms, including their preprocessor Atoms View? And also our nonlinear solutions. Now, we're not actually calling out a product because actually there's 2 in here, both Nastran Sol 400 as well as MARC for advanced nonlinear analysis. So we'll be talking about all of that later on this year. All right. Now, a few of you also said, well, what about my specific industry? And we said, okay, well, let's take probably some of the most popular ones and the most asked about ones that are currently using MSC Apex. And the 3 top ones are space applications, aircraft conceptual modeling, like internal loads and conceptual aircraft sizing, and automotive applications. So things like mid-surfacing and shell meshing for, say, like a LS Dyna crash model, or if you have an injection molded plastic part or something like that that you wanted in the automotive industry. So those are the 3 that made it there. Now, the last one that we wanted to talk about, kind of the one that just stuck out like a sore thumb, doesn't really have a whole bunch of other series type of webinars, but is no less important. In fact, it's asked about at least probably once a week, if not multiple times per week. Is the Python API built in within MSC Apex. And so the very next one, we'll have one of our guest speakers talk about the Python scripting and utilities commands, both from a pre-processing as well as interoperability and maybe even some post-processing scripting as well, if you guys are lucky. Okay? So stay tuned for that. We've got some exciting ones. Now, let's talk about what the 2021 releases look like, okay? So we've switched from 2 releases per year to 4 releases per year, okay? So every 3 months, you've got a brand new release of MSC Apex. Some of you have even been involved in our beta testing program. We extend invites to a select number of longtime users of MSC Apex to become our trusted advisors for the future of the product. So you'll be getting emails about that 4 times per year. Okay, now previously when it was only twice a year, we had a live webinar, much like this one, for each new release. Now, since then, MSC has acquired a number of different products, as well as switching to 4 releases per year. We just figured it was just too much to have a live webinar for the beta and a live webinar for the GA release 4 times a year. And most of you guys, Apex is not the only tool that you use, so you're attending live webinars for Nastran and Atoms and MARC and other tools as well. We just thought it was just too much. So we decided, instead of requiring you to attend a live webinar, instead we are doing 2 things for Apex and for other products in our portfolio as well. For the products that have a lot of features and functions and a lot of development going on, we're going to do 2 videos. For the lighter releases, we'll only do 1 video. But for Apex specifically, because there's so much hot and heavy development happening right now, we're going to, for each release, we'll have 2 videos come out after the release comes out. We'll have a highlight reel, which for those of you that have a very tight schedule, just watch that one and you'll see a very quick 5-minute overview. And then video number 2, we'll have a technical deep dive. Now, this technical deep dive is sometimes 30, sometimes 45, sometimes an hour long. But this is basically replacing that What's New webinar that you guys are used to, okay? All right, so I am one of the product marketing managers here at MSC Software. I specifically focus on the GUIs for the structural analysis products. So Apex, Patran, CAE Fatigue, as well as our platform Sim Manager for your PLM technologies. So I am the host for today. So just a quick reminder, we've got a very lively Q&A going on. You can send a question privately or you can send a question publicly. Feel free to send those at any point in time during the webinar. The quick questions, I might just fire back a quick response, or if you have a question that you specifically want to ask Steph, or you want me to ask Steph live, we'll do a Q&A session towards the end, and I'll gather all those up towards the end, and I'll ask Steph. Okay. Our presenter today is Dr. Steph Evans, who is one of MSC Software's esteemed international partners located in the UK. Most of you know him through his company, Evotech CAE Limited, or maybe even you know him from one of his amazing LinkedIn posts, which he's quite good at. Steph has actually spent the last 5 years running his company, Evotech, which, if I can say, offers an amazing set of training classes in MSC Apex. So if you haven't seen that, check that out. But before that, he actually spent 20 years in the aircraft industry. So he spent 20 years in the Airbus and the BAE Systems supply chain, doing exactly what we're talking about today, which is FEA development, analysis, and verification. Okay. So for that, I will go on mute and I will pass it over to Dr. Evans. Yeah.
Okay. Thank you, James. You can hear me okay?
Loud and clear. Right on.
Perfect. Okay, good morning, good afternoon, good evening, everybody. Thank you, James, for the introduction. My name's Steph Evans. I'm speaking today from the UK. We've got a beautiful spring day. The winter is finally over, I think, so everybody's smiling here. Okay, so I'm going to run through a number of aspects of the webinar today, focus on mid-surfacing and shell meshing. I'm just going to give you a quick overview, and then we're going to run into a series of how-to videos outlining some of the techniques that we'll talk about. Okay, so we're focused on a typical aerospace component. Many of you who've worked in the aerospace industry will be familiar with this type of structure, maybe a rib or a bulkhead, thin wall machining, sometimes known as a shear panel. Lots of different changes in thickness, lots of features, fillets, holes, steps, lots of entities to consider from an FEA model build analysis and verification perspective. Okay, so I'm going to run through 2 workflows. So the first workflow is going to be focused on what we call CAD to results. We used to talk about CAD to mesh, but Apex offers much more than that now. So we're, the full cycle, or product development cycle, if you like, for an FEA model, from source CAD, geometry preparation, mesh definition, and then finally attribution and verification through to a fully running model, whether the analysis is performed in Apex or externally using one of the tools that James mentioned. Okay, we're going to look at a second workflow as well, and some of the tools that you may or may not be aware of in Apex, looking at a legacy FEA model and what we call orphan model manipulation. So this is the situation where you've got maybe a legacy Nastran or legacy FEA bulk data file, and you can bring that into the Apex environment and manipulate it with no geometry in there whatsoever. Okay, so just a couple of approaches that we're going to work through today. Okay, so let's get started. The first one, workflow 1, CAD to results geometry preparation. So I've listed out a number of tips here. This is a best practice webinar, so we want to try and focus the mind on some of the things that will make your user experience as efficient as possible. So just listen these out, keep things simple. So important geometry, good practice to clean geometry before you start, to get rid of any errors or bugs in the geometry, and we've got simple tools in Apex to do that. Don't defeature when you don't have to. So taking this shear panel as an example, we've got lots of fillets and details in there. We're ultimately going to be generating a mid-surfaced, mid-surface surface, as it were. So there's little point in spending a long time defeaturing solids if the target model output is surfaces. Okay, and then during the manipulation, it's probably good practice to delete unnecessary vertices and edges. So to try and simplify the geometry as much as possible to get us back to our bare bone surface for mesh development. Okay. Second tip, automate when you can. Okay. So there's many different techniques in Apex. Just focusing on one here. So when we do the mid-surfacing, there are lots of surfaces that get stitched together. We've got tools like Vertex Edge Drag. These are generally manual tools. So if possible, use automation where you can. And I'm talking automation within the Apex user interface. I'm not really talking specifically about the Python API here, but obviously there are opportunities for that kind of automation. And we'll probably cover that on the next webinar, as James mentioned. So yeah, extend stitch where possible. Use the appropriate auto mid-surfacing tool to suit your geometry complexity. So again, we'll see this in the example, but there are some simple tools for working with simple geometry, and then some more involved tools for looking at complex geometries where we've got lots of T sections, lots of joined and featured regions within the solid and then surface geometry. Okay. Tip 3, be clever with the display options. So Apex has really got some sort of state-of-the-art visualization tools. So you can use things like auto color to color individual entities in an automated sense before stitching, so you can see what's tied together, what isn't. We've got things like transparency mode, so you can overlay a transparent 3D solid over the mid-surface, and then you can sort of look at T-junctions, cruciforms, and that type of thing to see how the idealized surface relates to the master solid geometry. Okay, so just going to run through a couple of approaches for mid-surfacing and shell meshing. So we're going to import some geometry that we've got access to. This is, as you'll see, a machining typical of an aerospace type component. So a shear web with a series of horizontal and vertical stiffeners, and then a flange across the top, a series of fastener holes around the edges, machining detail, a lot of the fillets, some local pockets, and then some boundary holes in there as well. So we're going to try and capture all these elements, all these entities within a mid-surfaced and shell meshed model. So you can see in the browser we've got this single solid object. Good practice to clean up the geometry before you start, just to make sure there's no sliver surfaces or gaps or anything like that, or sliver faces I should say, within this solid definition. So we've cleaned that up. Again, single entity in the browser. So we're going to look now at some mid-surfacing. So a whole bunch of different techniques in Apex, but we're going to use the incremental mid-surface for something like this, where you've got multiple surfaces to be generated. So we pick the body, right mouse button, sorry, the middle mouse button to accept. The algorithm runs through, and Apex is looking for matched top and bottom faces across these discrete regions of the model. So it's color-coded things. Okay. Let's just run with that, shall we? Just going to merge some of those faces together, so you can see here for these webs, they're different colors. So if we merge them together, you will see them as a single entity, and may simplify things for us when we get through to the mesh stage. Okay, I'm doing this live, so talking and on the rating and doing at the same time. Middle mouse button to accept. Let Apex run through and see what we've got. We had the defaults turned on for the definitions, and if we turn on the edge display, you can see we've got these three edges shown in red and the shared edges shown in yellow. We're going to colour code each discrete object, each discrete surface, so you can see those. The bulk of the horizontal and vertical stiffeners are not connected to the green shear panel at the moment, so we can use the extend surface tool, just using the defaults here. Select all the surfaces, middle mouse button, and then see what we've got in terms of the definition. Okay, so we've got a single general body. So there's the solid, there's the mid-surface general body is generated. Okay, just by visual inspection we can see there's a couple of issues up here. Okay, so there's a gap there, so I'm just going to drag that edge across. We've got a fillet surface that's been generated by the mid-surfacing operation, so I'm just going to change the filter selection to faces and then delete that. It looks like we've got some of the shared surface in here as well. Okay, we've got some edges we perhaps don't want. Again, change the selection to edges, remove those, just work your way around. Pretty simple type of operation here. Okay, so it won't lose that edge, so there must be some vertex definition in there. So what we can do is simply move these vertices across, like so. Right, so pretty clean mid-surface, really easy to get hold of that. Okay, if we look at the cruciform, as it were, where these regions come together, you can see here, let me just show you top view. So here we've got good definition, but here there's a mismatch between the two stiffeners. Now if I show you the underlying solid, that is in fact a sort of byproduct of the geometry. Generally speaking, you'd want all your stiffness to line up, so whether that's a mistake in the CAD or whether there's some kind of systems assembly that just hasn't got room in there, but we're going to make that modification. So if we hide the solid, I'm going to create what we call a filler surface from here to here. Okay, so we've got a new surface that's attached. Okay, and then I'm going to extend that new surface up. Okay, and then I can use the edge of the old surface to do the split. So I'm doing a split with a curve. So just pick these curves, right click, and then select continuous edge, and it does that for me. Okay, I can then delete the old face. Okay, it won't let me delete this. Yeah, there's a gap there. Okay, so I'm just going to close that gap. So run the vertex across, and now this is a face I can lose. Okay, let me see if I can delete these lines. Let me just change the selection filter. So yeah, the selection filters are really handy. You don't need to go back and forth between lots of different forms to change these selections. There you go, so deleted those edges that I didn't want. It's got a pretty good definition now of the underlying surface. If I show the solid in transparent mode, So in the model browser, if you just click on the icon and then switch to transparency, crank this up to 80% transparent, maybe turn off the vertices just to keep the display more straightforward. There you go, you can see the surface definition. So let me make the, if I make this white, there we go. You'll see that better. Okay, so you've got all these cruciforms. Obviously, we're not modelling the fillets. Well, perhaps it's not obvious, but in this case, we're not modelling the fillets. That doesn't really make sense from a shell element perspective. If you were to look at fillets, you'd probably want to be using a solid model definition. But yeah, pretty clean. A couple of things I noticed then. So here, where we've got this hole, we've got a thicker section. Just turn transparency off. We've got a thicker section representing this ring. Okay, so I want to split this surface with this edge. Okay, there you go. We've got the split there. I'm not worrying too much about the fillet edge because obviously this is a 2D representation. Same again here. I'm going to have change in thickness, so I need to split the surface. So pick the pick the surface, pick the solid. Again, select contiguous edge, and then we've got that surface split. Okay, and I think there's a couple more just at this end as well. So we want to split this face and this face with this edge. Actually, we could have done that in one step. This face with this edge. There you go. Notice I'm not doing any meshing yet. And then I can drag that edge across. Can you see the construction lines as I move? So I can ensure that I'm keeping it straight and it'll hit that edge. Okay, so really nice, powerful way of moving and manipulating those entities. Okay, I'm going to, what's often useful here is you've got lots of detail, lots of vertices and what have you. I tend to try and get rid of any additional vertices first of all. Okay, switch that to vertices. Okay, so it's going to get rid of any vertices that we don't want in the model that could conflict with the meshing algorithms. Okay, and that's pretty much the geometry for the mid-surfacing ready to go. Okay, so we now look into the mesh definition now that we've got the mid-surface defined, and we're going to look at a couple of tips here. Geometry is your friend. Okay, so we're going to use in this model we've got a series of fastener holes around the periphery of the shear panel. So by defeaturing those physical holes, we can create hard points at the hole centers. Saves us a number of mouse clicks for mesh development. And then bear in mind that geometry modification, mesh update, and element quality display is all generative. So some of you may not be familiar with this, but basically means that if you change the geometry, then all of the model attributes, mesh properties, loading, and what have you will be updated accordingly. Okay. Tip 2: mesh itself can be used to highlight problems with geometry. So if you had a very small sliver surface in this geometry, you can use a rudimentary 2D mesh and then the GRO 2D mesh, 2D 3D mesh to highlight any problems. And then we can use the mesh topology to show the edge status. So similarly here on the image that we've got top left, this is geometry where we've got red, green, and yellow lines. We can do the same thing for the resultant mesh to show the edge status as well. That can help us understand the underlying geometry. Okay. Tip 3: controlling the mesh. So we've got what we call feature mesh settings. So we can control the mesh at things like holes, fillets and chamfers, etc. So we can do that on a global basis and set different parameters for different dimensions. So that works nicely if you've got a complex model with lots of different size features in there. Bear in mind that you can use multiple meshing algorithms. So talking specifically about 2D shell meshing, we've got the auto, the pave and the map meshing algorithms. And that bear in mind we can mesh single faces rather than over and above the whole surface by using the lower dimensional entity selection filters. Okay, so we've got the surface geometry that we've extracted. We're going to do some meshing. If I measure typical dimension, so let's have a look. We'll measure between two adjacent holes. So if you hover over the edge, you get the center point, and then to another edge and the center point. So you've got 24 mil. So we want, I don't know, 4 or 5 elements across there. So if we go for a 5 mil element edge length for this model representation, that'll work quite nicely. Okay. So a couple of things with meshing. Obviously, we want to use it for defining the underlying FEA model, but it can be useful to show any problems with the underlying geometry. All right. So if I set the mesh size to 5 mil and then a mixed auto algorithm, develops the mesh very quickly, and then I'm going to now check the element quality. Okay. So you can see here, green elements are good, poor elements in yellow, bad in orange, and then we've got one invalid element. Okay, so one element in that model is problematic. It'd be quite difficult to find that using legacy means. So if you just simply right-click on that bad element and then click on Isolate and Enhance, it gives us the geometry with the single bad element shown. Obviously, it's still difficult to see that bad element. So we've got this Grow 2D Mesh button here. So we just grow the 2D mesh. So we know there's a bad element in there somewhere. If we look, there you go, there it is. So there's something happening with that geometry. So if I turn the vertices on, I think it's as simple as just moving that vertex back to there. There you go, and all the bad elements have disappeared. Okay, so hit the view, the element quality view. So we've now got no invalid elements. Okay, so really straightforward to work our way around to that within the model. You can see we've got lots of bad and poor and bad elements at the moment. So obviously, lots of these are around the fastener holes, given the mesh density that we've got. For this type of model, probably wouldn't mesh in the fastener holes. We'd probably just defeature those holes. Okay, so again, pretty nice way of doing this. So again, under the geometry edit tools, this defeature tool, so you've got multiple options. So if we do it by defeaturing by identified feature, pick the object, middle mouse button to select, and then it shows us it's found a number of different things. It's found 2D holes and 2D fillets. We're not too concerned with the fillets, but you can see it's got a series of holes with a diameter above 19 mil, and then a series of holes with a diameter below 19 mil, which are these fastener holes. So if you simply click on the entity set you want to get rid of, those will then turn orange, middle mouse button to accept, and they're all gone. Okay, I did miss a step there. I'm going to go back. I forgot to click on the create seed point in defeatured hole. Okay, so do that. There you go. So in the browser, it's created all these seed points, and the mesh is updated to reference those entities. Okay, so Apex is generative. So by changing the geometry, we've changed the underlying mesh and all that sort of stuff. in that operation. If we had materials and properties in there, they would have updated as well. So that's the meshing stage. So pretty reasonable mesh definition. Again, we can check the element quality. We've got, let's have a look. Got mixed quad and tri mesh. We've got some poor elements, some bad elements, but nearly 7,000 good elements. So massively good quality element dominated. Okay, so I'm going to just show you a couple of tricks now to deal with element quality. So in these regions here where we've got the, let me change the colour of these points to make them a bit easier to see. So I'm going to turn those red. There you go. So here we've got a square panel with these fasteners. We've hit the fastener nodes, but we've got, well, it's not particularly irregular, but we have got some irregularity around the edges. So when we surface mesh, we can do this based on a full surface or a series of faces, okay? And then we've got all the different algorithms that we might want to look at. So what I would tend to do is mesh the whole structure with a mixed mesh using the auto algorithm. And, but for these detail regions, I'd probably switch to quad only with a mapped algorithm, okay? So just select that and it updates, and we've got a much better mesh definition. We've hit all the fastener nodes. So really just a case of working our way around and getting those, actually we'll do those all together and then we'll get better definition. There you go. Okay. Some areas it doesn't work so well, so if I do this, there you go. That would definitely be better with the mixed algorithm. Yeah, that's probably better with the mixed as well. The mixed gives you regular quads and then a transition with tris. But where we can, we'll use quad only to give us the quality that we want. Okay. Try it here. Yeah, that's better. So just working our way around visually, eyeballing the model. Okay. We might have a definition. Let's have a look. We'll just try this in one place just to see what where we've got a drop off here. So we can go in and split the surface. So pick the surface, pick 2 points, and it updates like so. Okay, so slightly better definition there. Do the same here. Okay. I need to remesh that actually. We'll do it with the auto, and then we'll tidy up these regions with the pave. Excuse me. So now for auto execute. For some reason it doesn't like that, so I'm just going to go undo a couple of steps. Multiple undos in Apex, of course. Where are we? Yeah, that's back to where we were. Okay, and we've got rid of this one here. Okay, so we can play games with the meshing algorithm. There you go. And then once we've done all of that, we can then check the element quality again. Okay, 7,000, exactly 7,000 good elements, 38 poor, 4 bad. Okay. Bad elements will run, invalid elements won't, so we need to make sure we've got no invalids. So you can see here we're using the, what's it called, the mesh flow optimization here to give us this nice distribution across these discrete regions. Okay, so you've got lots of tricks you can play with these models, but we get to a pretty good mesh pretty quickly. Okay. So now we've got the mesh developed, we can start to look at attribution and verification. So a couple of things here. One aspect of mesh development or shell meshing is that you need to consider your surface normals and your XY directions for the shell. So every shell element has a local coordinate frame. X and Y sits in the plane of the shell, and then Z points normal to that XY plane, if you like. So it's good practice to ensure that you've got normal consistency, and then you can think about direction. We've got something called the dual color display option, which we'll see, and then it's again useful to think about how you control the X direction that the shell elements are pointing in. So you want to try and get those things set before you move on to things like property definition. Okay. You can automate and visualize your properties. So we've got a pretty nice automation tool where we can build shell thickness and offset information from an underlying 3D solid. It's good practice to use the force constant thickness when auto-generating shell properties. What you probably don't want to have in this kind of model is to have different shell thicknesses where you've got discrete fillet features. Okay, and then once we've got that, you can use the section view tool to do all sorts of things, display and edit those properties that have been created. Okay, if you're going to be exporting your model, then it's probably a good idea to control your node element coordinate frame and material IDs to avoid external clashes, I should say. So if you're building a portion of a structure that's going to go into a master model definition, you may well have an ID range which your entities need to sit in. So you can control and modify those within Apex pretty easily. And then this is, if I was going to say anything, this is probably the most important tip of all the stuff we're going to look at, or we've been looking at today. So use the analysis readiness tool to understand if you've got any pre-analysis issues, and then irrespective of whether you're going to be solving in Apex or exporting the model externally, I would suggest it's good practice to always use, or rather always simulate, normal mode response for both parts and assemblies using the Apex Structures solver, just to make sure the model deforms and stress distribution develop, or strain energy develop in a way that is expected for the type of structure you're looking at. Okay, so once we've got the mesh definition set up, we now need to think about materials and properties and that kind of thing in the model. Okay, so the first thing that we would generally do, we perhaps have a look at the overlay between the mesh and the CAD again. Again, turn off the edges, turn off vertices. Okay, so we can see all that relationship. Okay, I'll tell you one thing that I didn't look at, which we can do now, which would work quite nicely, is to look at the mesh topology. So we looked at the geometry topology, the edges and the like. So if we look at the mesh topology, we can see where the free edges are relative to the solid. If I just hide the underlying surfaces, there you go, pretty nice definition there. So the coloured lines, the red, yellow and green lines, all relate to the underlying shell mesh versus the transparent view of the CAD model, the solid CAD model. Okay, so if I show you the mesh on its own, there you go, just changing some of the display options. So we've got red or free edges where we'd expect, and then shared edges, shared between two faces in green and shared between three in yellow. Okay, so that gives us a good heads up with what's going on with the model. So if I show the geometry, we're now going to look at the shell normals. Of course, each shell element has a normal direction. So before we look at the directions, I'm just going to look at a color code. So this button on the top here, shell normal dual color, shows us one face. I can't remember which way it is now. Let's have a look. So the bottom face is shown in this pinky red color, and the top face is shown in blue. Okay. So before we worry too much about directions, I just like to get the model consistent. Okay. So you can see here, if you look at these horizontals, there's a horizontal here which is switching, sorry, the stiffener going a different direction. Okay, so I'm going to go into ephemerid tools, and we've got element orientation, and I'm going to switch the orientation for those elements. So you just pick a single element and it switches for the whole face. Okay, same for the stiffeners in the other direction, so these are going in an opposing direction. There we are. Okay, so all the stiffeners in that plane are going one way, and all the stiffeners in that plane are going another way, or the consistent way. Okay, so happy with that. So once we've got the normal consistency defined, we can look at the normal directions. Actually, excuse me, that wasn't the normal direction. Here we are, shell normal vector. So currently we've got all the normals pointing outwards. We could use them to point inwards if necessary, so we're just going to use the orientation again and then pick all the elements, so flip them over. Okay, so the colours are updated and the vectors are now pointing inwards. Okay. We might want to look at the element orientation, so sort of separate from the shell normal orientation. The element orientation is the local element coordinate system, again using red, green and blue. And if you're ever unsure what red, green and blue mean, you can pick them up from the global frame, or coordinate frame defined here. So red is always X, green is always Y, and Z is always blue. Okay, so a couple of things we can do here. Just make sure I've got the surface turned on, which I have. Go back to element orientation. So we're now looking at the definition. So this, we can either define the orientation along a vector. So I'll just show you how that works. So if I pick all the elements and then pick an edge of the geometry, so we've got the vector normal, and then look, all of those local x-axes are now aligned with that vector. Okay, and it does the best it can where you've got curvature. Okay, you can see that. Another approach might be to look at elements aligned with curves. So if we pick all the elements and then pick the surface edge, right click, select contiguous edges. So we've now got the edges defined all the way around the structure. Middle mouse button to accept. And X will now follow the external edge in all cases. Okay, so it's having a little bit of a think here, but we can see that. So yeah, X is coming along this edge, and then effectively turning the corner when it goes round, like so. All right. You can do this for full surface, for discrete faces, and for discrete elements as well. So there's various games you can play there with shell orientation. Okay. So what we now need to do is define shell properties. So we've got a couple of tricks we can do here. We've got the ability to show, if we bring the solid into view and then go into attribution, we've got this auto thickness algorithm. Okay. I tend to use, for this kind of thing, where we force a constant thickness. What we're trying to avoid is having transition in thicknesses where we've got fillets. You can see that. Oops. Just go into the view. So where we've got a fillet, we perhaps wouldn't want to have different property sets across there. Okay. So by using the force constant thickness option, well, you'll see what this does now. So pick the surfaces, pick the solids, middle mouse button, and then Apex is calculating the thickness range for those discrete entities. So it's just, you can see in there, let me just hide this for a second and then switch it to full 3D view. There you go. So you can see the thickness ranges that have been calculated against the geometry. Okay, so we've got lots of different thicknesses in there. Okay, it's done a good job at this boss section, if you like. You can see there, again, another change in cross-section. So I've had experience of trying to do this stuff manually, and it's pretty painful, to be honest. So having an algorithm there really helps a lot. Once we've got those sections defined, if you go into the model browser, we've got this section view, and we can use that to look at the definitions as they're color coded. So at the moment we've got different section properties for this stiffener, for example. So if we switch the selection to element, find out which property it is, click on assign, and now we can assign that property to any face we select. Okay, and we can repeat that all the way around the model. Okay, obviously this, well, I don't know for definite whether these sections are the same thickness, but if we let's just have a quick look. So here we can assign this section there we go. Okay, so you can play games with that kind of thing to build up the section definition that you want. You may see things like this where a thickness has been calculated and it's given it a very, very small offset. So the mid-surface in operation is slightly off compared with the average of the CAD faces. So in that sense, we might go click on assign. When it brings up the section property, we may click on create section. Apologies, where's that gone? 7. And let me do that again. I'm going to delete that one. Yeah, if we double click on it, we can change the value from a very small number to 0, and we can see in the browser that's been changed. Okay, so you've got full control of the tabular data and also the properties as you're working your way through this as well. It's a really nice way of doing it. Okay, so we'll come out of section mode, and now we'll have a quick look at defining material. So we've got multiple scripts for this kind of thing. So we've read some materials in from the script, and then it's just a case of assigning a material. So we've got, I don't know, 7075 aluminium, say, assign material, drop that onto the full part, and we're good. Okay. We can then look at numbering, renumber the entities, 10,000 series, pick the part we want to renumber, middle mouse button to accept, and then we can just go in with the cursor and show that we've got, where are we? Sorry, the probe tool or the cursor. So there you go, 10,000 series. Okay. So once we've got that defined, we can then look at what we call analysis readiness. So if we right click on the part, place it in the analysis scene. Got some issues here, missing constraints and loads. But if we switch to normal modes, and then we can just simply run the model. And it's completed successfully. Just double check the mode shapes. So I'll put the fringe on for, say, strain energy. Makes more sense for this type of thing. And then we can animate the different modes. Okay, so mode 7, first elastic body mode, mode 8, mode 9. Okay, and of course we can export the model, and we're done. Okay, so one final part of the workflow, looking at Orphan model manipulation, and this is where you've got legacy BDF definition or legacy FEA model. So tip 1, old is the new, as it were. So you might have a legacy certification BDF. So typically speaking, Nastran or external FEA data isn't always stored with CAD geometry. So if you've got the FEA model, don't worry. You can build and manipulate as you see fit. Okay. You can generate the appropriate geometry form. So we've got two types of mesh, CAD can be derived from mesh. We can create faceted bodies, which follow the mesh form, and we can create NURBS smooth geometry if we want to look at higher fidelity meshing. Okay. Controlling the legacy model. So you need to set the appropriate unit and assembly options when you import a model, and then we can look at local remeshing of that geometry or those facet bodies, and it will retain the legacy mesh away from the region of interest. And something useful to bear in mind is that the shell properties are remembered through the manipulation. Okay, tip number 4, you're good to go. Any geometry generated from legacy mesh can be exported to CAD. Okay, so we're going to have a look at a slightly different approach here, whereby we're going to build a new model using a legacy FEA reference as the baseline rather than geometry. Okay, so we're going to import an FEA representation, and this is the same shear web structure that we just saw. So we're going to specify the units and the organization. So import that into Apex. Everything's brought in nicely. So we've got the elements and the shell thicknesses and materials and what have you, both available to look at in the display and also in the model browser. Okay, so lots of shell sections, single material. Okay, that's the mesh body. All right, so we're going to bring in, just for reference, the geometry of an existing rib, or well, let's say an existing but a different rib to this, or different shear web to this, I should say. So bringing in this geometry, so we just browse to that location. It's a shear panel hole, so I think you'll probably be able to guess what's coming. So there you go. So we've got a new shear panel that's had some system access holes punched into it. Okay. We could obviously run through the full build that we saw with Apex a moment ago, but we're going to try and use the existing mesh to give us some kind of heads up on this. Right. So if we go into the geometry edit tools, geometry from mesh, okay, pick the mesh, middle mouse button to accept. It gives us all the regions it's found, if you like, in terms of unique faces, and then we can just go through, hit apply, and then in the browser, under the part that came in as the mesh, we now have this faceted body. Okay, so this is a geometric entity that's been created from the mesh, and you can see in these corners, obviously the original CAD would have had a nice clean fillet edge to it, but the mesh didn't, so the faceted body doesn't either. Okay, we do have lots of tools to create smooth geometry, but for this example I'm just going to show you what we can do with the mesh definition. All right, so we've still got the properties defined. So if we look at the new part that's come in, so really all we're going to do is split the underlying mesh with these the edges that make up these holes, and take it from there. Okay, so geometry edit tools, split surfaces, split using a curve. So we pick the facet body face, so we're not picking elements as such. Middle mouse button to accept, and then we can pick the edges. Okay, and it's made that split. If I just hide the solid for the time being, there you go. There's the split. Okay, so I'm going to repeat that for the other regions. Just run through it quickly. Do it from the back. Okay. And get rid of the geometry, and then we can delete those faces, So there's been a local remesh gone on these edges. We check the shell properties. They're still in there. They've still been maintained. Okay. We can look at tidying up the boundary mesh in those regions. Let's have a look. Just see what this does. Yeah, much better definition. Clean things up nicely. There we go. So, tidied things up. And then we can look at the thickness again. So we've made the modification with minimal effort by using the underlying legacy mesh as the sort of surrogate geometry for the manipulation exercise. So, in summary, some of the best practice stuff that we've got from geometry preparation. Keep things simple. So, talked about cleaning geometry before you start. Don't defeature where you don't have to, and then delete unnecessary edges and vertices. Automate when you can. So use tools like extend and stitch where possible to speed up your workflow. Use the appropriate mid-surfacing tool to suit your geometry complexity. And then thirdly, tip 3, be clever with your display options. So use auto color within the model browser and use transparency to compare your 3D geometry with your underlying mid-surface and shell mesh definition. Okay. From a mesh definition perspective, geometry is your friend. So you can defeature your geometry and create things like hard points at fastener holes that the mesh will be forced to follow. Mesh can be used to highlight problems with the geometry. So if you remember, we looked at a mid-surface where the we had a cut edge that wasn't visible but only became apparent when we looked at the mesh quality. And then we can control the mesh with things like feature mesh settings, using the appropriate algorithm and meshing with low dimensional faces. Attribution and verification, orient your elements both in terms of shell normals and shell XY direction. Automate and visualize your properties. So use the section mode to look at your property sets and how they're distributed in the model. And then finally, check that your model runs. This is probably the biggest tip of all, I would say, using the Apex structures license. And then finally, looking at Orphan model manipulation, you can use the tools to create the appropriate geometry from a legacy PDF file. And you're good to go in the sense that any geometry that you create, you can then export to an external CAD system. Okay. So that's the conclusion of the slide presentation, the demonstration I wanted to run through today. Run over a little bit, but we've still got probably about 10 minutes left for questions and the like. Are you on the call, James?
Yes, I am. All right. So we've had a very lively Q&A over here, and we're probably not going to be able to get to them all. So I apologize ahead of time. But some of the really cool ones that came out, I'll read them to you, and you can answer for me. So the first one is, let's say you have a solid piece of geometry. Can you actually draw on that solid body and create geometry, not just import CAD?
Absolutely. Yeah. So Apex has a full suite of sketching tools. And it also has things like push-pull, some of the direct modeling functionality, which you can use to create 1D, 2D, or 3D geometry, either freestanding or connected to your CAD model that's come in.
Awesome. Thank you, Steph. We've had a number of different questions asking about automatic parameter updates, whether it's thickness, whether it's mesh, whether it's all sorts of things. So I'm going to kind of combine some stuff, but the question itself is, when the geometry or the location of the mid-surface changes, walk us through a little bit about how Apex automatically updates that.
Okay, well, I'm not going to run through that live on Apex, as it were, but if you were to change your mid-surface position or the position of the geometry, or indeed a section change, then you can either use the the auto thickness tool to repopulate your shell properties, or you can manually go into the section view tool and change thicknesses and offsets in there. But both of those are generative in the sense that they will wash through the model and any mesh that's already on there. Okay.
Perfect. Thank you, Steph. And that was a good lead in to, I'll throw a comment in here too, which is no matter where in the world you are currently located, if that question kind of sparked your interest and you have more interest in seeing it live, please reach out to us, mscsoftware.com, or any of your local application engineers or your account manager, and ask for a demo of this, because there are Apex specialists in pretty much every country around the world. And if there isn't, we'll get one close to you, and we'll have a nice long 2 or 3 hour discussion, and we can go as deep as you want with mid-surfacing and shell meshing and automatic updates. That's a question that's really kind of difficult to answer in a quick 5-minute question. All right, so the last one that we'll do, and then we'll cut it off for today, which is during your demo, you did a certain amount of mesh customization. Can you parameterize those mesh settings?
Absolutely, James. Yeah. So we've got the feature mesh settings. So if we wanted to maybe repeat a ring of elements around a fastener hole or around a 2D fillet or chamfer or something like that, we can control those types of things. And equally, they're all applicable to 3D meshing as well. So you don't need to be spending long time manually mesh controlling these things through the use of the feature mesh settings.
Perfect. Awesome. So I'm seeing we're still getting more and more questions. So please don't hesitate. We're out of time today, but please don't hesitate to email us or contact us. Steph.evans@evotechcae.com or james.pura@mscsoftware.com. Or basically anybody that has an MSC or Hexagon email address. Just email us and we'll somehow get your question answered as quickly as possible. All right, and we can do some demos and all sorts of good stuff. Thank you, everybody, for attending today. You will be getting an email with the recording afterwards, so that you can feel free to send that on to your colleagues. And also feel free to send, if you like this and you think that some of your coworkers want to see it as well, please forward the invite to them. And we'd be happy to see them on a following monthly webinar. Okay, thank you very much.
Thank you. Goodbye.